Hello everyone and welcome to TalentSprint. Our discussion in this session will be on triangle and its properties, which is a part of geometry. Geometry, as you all know, is a branch of mathematics that deals with the study of shapes, figures and its properties. And this is one of the oldest sciences which goes back to the times of Euclid, Pythagoras and other great philosophers and mathematicians who have contributed to this field. As such, geometry is a vast subject, but keeping in mind the type of questions that we get in various competitive exams, we shall limit our discussion only to plane geometry. Now, what is plane geometry? Plane geometry deals with plane figures like triangle, quadrilaterals that include a square, rectangle, a parallelogram, rhombus, trapezium, etc., and circles. So primarily plane geometry is the study of plane figures and its properties. And in this particular session, we shall focus on triangle and its properties. Now, before we learn anything about triangle or any of its properties, let us understand a few important terms relevant to geometry. The first one here is point. Now, what is a point, or how do we define a point? In simple words, point is the most simple geometrical shape, right? Point is the simplest geometrical shape that can be drawn, and it has got no size, right? So point is the minimum of all the different geometric shapes that we have, right? The simplest geometrical shape. Next comes a line. What is a line? Well, line is a collection of infinite points, right? A line is described only by its length, but it has no breadth, right? So no breadth or negligible breadth, but only a length. And on this length, we have infinite points. So line is basically a geometrical shape that is described only by length, and it has got infinite points on it. It extends up to infinity, right? The next one here is line segment. Now, what is a line segment? Well, as the name says, line segment is a part of the line, right? Line segment is that part of the line which falls between the two given points, right? So the difference between a line and a line segment would be that a line extends up to infinity, but a line segment has a defined length, and it is of that length which falls between the 2 points. Okay, and it has all the other infinite points in between the two given points there. Now, after learning about line and line segment, the next one is a ray. What is a ray? Well, ray is also a line segment, but it extends up to infinity, right? Ray is a line segment that extends up to infinity in one of the directions. It is basically a unidirectional line segment which goes up to infinity. And the last one here, before we look at triangle and its properties, is angle. Angle again is one of the most important terms when it comes to geometry. What is an angle? Well, angle in simple words is an angular distance, right? It is the angular distance between the two rays which meet at a common point, or when two lines intersect at a point, we find different angles there, right? And each angle defines the distance between the two lines or the two rays that are connected through a common point. And not just for lines or rays, even when two planes intersect, let's say there are two rectangular planes which intersect right at some point or in some direction there, right? Now, even when two planes intersect, we find some angle between them, right? Or some angular distance between them, which is nothing but the angle between the two planes. Now, based on measurement, angles can be classified into various types. For example, an acute angle. What is an acute angle? It is between 0 degrees and 90 degrees, or an angle less than 90 degrees is referred to as an acute angle. Then obtuse angle. What is an obtuse angle? Angle greater than 90 degrees but less than 180 degrees, right? So an angle between 90 and 180 is an obtuse angle, and between 0 degrees and 90 degrees is acute angle. What is a right angle? Right angle is exactly 90 degrees. Next comes a straight angle. Straight angle is 180 degrees, right? So any straight line, if you take, the angle there will be 180 degrees at any point. So that's called a straight angle. And next one is a reflex angle. Reflex angle is between 180 degrees and 360 degrees, right? Greater than 180 and less than 360 degrees is a reflex angle. What is a complete angle? Well, complete angle, as the name says, is complete angle, right? 360 degrees. So an angle of 360 degrees is called a complete angle. So based on measurement, the different angles are acute angle, which is between 0 degrees and 90 degrees. Right angle, exactly 90 degrees. Obtuse angle between 90 degrees and 180 degrees. Straight angle exactly 180 degrees. Reflex angle between 180 degrees and 360 degrees, and a complete angle is 360 degrees. Also, there is something known as supplementary angles and complementary angles. So what are these two types of angles, or what is meant by complementary angles and supplementary angles? When two angles add up to 90 degrees, these are referred as complementary angles, right? When the sum of two angles is equal to 90 degrees, then the two angles are called complementary angles. And when the sum of the two angles is 180 degrees, then the angles are called supplementary angles. For example, 60 degrees and 30 degrees. What is the total? 90. 60 plus 30 equals to 90. So these two angles, 60 degrees and 90 degrees, are complementary. Likewise, 85 degrees and 5 degrees, complementary angles, right? Supplementary should add up to 180 degrees. So for example, 150 degrees and 30 degrees. What is the total? 180 degrees. So 150 and 30 degrees are complementary angles. Likewise, 179 degrees and 1 degree, right? 179 degrees plus 1 degree is equal to 180 degrees. So even these two angles are called supplementary angles. So angles, when they add up to 90, complementary, and when they add up to 180 degrees, they are referred to as supplementary angles. Now let us move on to the next part of the discussion, that is parallel lines, right? What are parallel lines? Well, parallel lines are two lines which would never meet each other even if they are extended infinitely, right? Basically the distance between two parallel lines is constant throughout their length. So here, as you see, these two horizontal lines can be called parallel lines, right? These two lines would never meet each other since the distance between these two lines is constant throughout their length, right? So let's consider the two parallel lines here as AB and CD, right? AB is the first parallel line and CD is the second one. And here we see a transversal. Now what is meant by a transversal? This is the one that cuts the two parallel lines, right? So let's say EF is the transversal. Okay, so two parallel lines are being cut by a transversal EF. Now if you observe at the points of intersection, there are 2 points of intersection here, right? It cuts the first parallel line at this point and the second one at this point, as we can see from this illustration. There are different angles at both the points of intersection, right? We see, different angles here. For example, let's say this is angle A, then angle B, angle C, and this is angle D. Likewise, at the second point of intersection, we have 4 angles. Let's say this is E and F, G and H. Alright, so A, B, C, D are the 4 angles at the first point of intersection, and E, F, G, H are the next 4 angles at the second point of intersection. Now there are a few properties with respect to the 8 angles that we see here, right? A, B, C, D, E, F, G, H are the 8 angles that we can see here. Now with respect to these 8 angles, there are a few important properties that we need to understand. So let's look at each one of them. Now the first and the most simplest one here is that there are various straight angles here. What is a straight angle? 180 degree, right? So if you look at combination of 2 angles here, we'll find many straight angles. For example, A plus D, right? Angle A plus angle D is a straight angle. Since it is like a straight line, the 2 angles should add up to 180 degrees, right? So these are straight angles, A and D together. Likewise, angle A plus angle B also also add up to 180 degrees, right? So a straight angle. Then D plus C, B plus C, and in this case here E plus F, F plus G, G plus H, E plus H. All these pairs add up to 180 degrees, which I'm sure is a very simple point and all of you are clear with it. Then there is something known as vertical angles, right? Vertical angles are always equal. For example, if you look at the first intersection, angle A will be equal to angle C, right? These are kind of opposite angles, or vertical angles is what they're generally known as. So angle A is equal to angle C. Angle A is equal to angle C, right? Likewise, angle D will be equal to angle B. Angle D is equal to angle B. Even in the second case here, we find that angle E and angle G would be equal and H and F will be equal. So angle E is equal to angle G and angle F is equal to angle H, right? So these are known as vertical angles. Next comes corresponding angles. Now what is meant by corresponding angles here? If you look at the first set and the second set, there are 4 pairs of corresponding angles. For example, angle A corresponds to angle E. right? Angle A and angle E are known as corresponding angles. Angle B and angle F are the second pair of corresponding angles. Angle D and H is the third pair of corresponding angles. And the last one here is angle C with angle G, right? So if you look at it, at the point of intersection, the angle above and on the left side is A. And here at the point of intersection, the angle above and on the left side is E. So corresponding, A corresponds to angle E, B corresponds to angle F, D to H and C to G, right? Now each pair of these corresponding angles are equal. So the second point here is that angle A is equal to angle E, right? We can say angle A equals to angle E. Likewise, angle B is equal to angle F. Angle B is equal to angle F. Then the third set can be taken as D and H. Angle D is equal to angle H. And the last one is C and G. Angle C is equal to angle G. So all these are corresponding angles. A is corresponding to E and they are equal. B corresponds to F and they are equal. D, H and CG. Next, we have alternate angles. Now, what are alternate angles here? There are two types of alternate angles: interior alternate angles and exterior alternate angles, right? Alternate angles are, on the opposite side of the transversal. For example, what are the interior angles of the transversal? Now let's first understand interior angles and exterior angles. There are four interior angles here. If you look at the transversal, interior angles are those which are between the two parallel lines. So B, C, E, H are interior angles, and exterior are outside the two parallel lines. So A, D, F, G are exterior angles. Now we have interior alternate angles and exterior alternate angles. So let's understand what are the interior alternate angles. Angle B and angle H are alternate angles, and these alternate angles are equal. Angle B is equal to angle H, right? Alternate angles are equal. Likewise, angle C will be equal to angle E. So we can say angle B is equal to angle H and angle C is equal to angle E, right? These are alternate angles on the alternate sides and interior because they are between the two parallel lines. So when we say alternate interior angles are equal, it must be clear. Interior and alternate. So C with E and B with H. These pairs are also equal. Likewise, we have exterior alternate angles, and I'm sure all of you are clear with what is exterior alternate angles, right? So angle A will be equal to angle G, right? Angle A equals angle G, and angle D equals angle F. Angle D is equal to angle F, right? So these are all vertical angles or opposite angles: A, C, B, D, E, G, H, F, right? So these are vertical angles, generally called as vertical angles. Alright, then how about AE, BF, DH and CG? AE, DH, BF, CG, all these are corresponding angles. So corresponding angles are equal. So these are corresponding angles. And next comes BH, CE. BH and CE represent interior alternate angles. So interior alternate angles, and we know that interior alternate angles are equal. And the last one here is exterior alternate angles, AG and DF. AG and DF. These are exterior alternate angles. So this shows the equality between different types of angles when two parallel lines are cut by a transversal. Now, apart from these equality between various angles, we also find supplementary angles in this illustration here, right? We have already learned that there are various supplementary angles, like AD are supplementary because their total is 180, right? A plus D is a straight angle. Likewise, D plus C is a straight angle. A plus B is straight angle. B plus C is also a straight angle. Similarly, in the second case also we find 4 pairs of supplementary angles. But then, apart from these direct pairs of supplementary angles, we also have a few indirect pairs. For example, angle B and angle E will add up to 180 degrees. Interior angles on the same side, right? We know that B, E, C, H are interior angles. Remember, interior angles on the same side are B and E. Always add up to 180 degrees. So B and E are supplementary. Likewise, interior angles on the other side are C and H. So C plus H is also 180 degrees. So we can say B plus E equals to 180 degrees and C plus H equals to 180 degrees. An easy way of remembering this is interior angles on the same side are supplementary. Likewise, exterior angles on the same side are also supplementary. Now, what are the exterior angles? A, D, F, H. Now, exterior angles on the same side, A and F, will add up to 180 degrees. So we can say A plus F equals to 180 degrees, and hence these are supplementary. Likewise, D and G will add up to 180. So D plus G is also 180 degrees. So this shows supplementary angles which are exterior and on the same side. The first two cases here show the supplementary angles which are interior and on the same side. And it is also very easy to understand why do we say that these are supplementary angles. See, from the equality we already know that A is equal to E, right? Here we see that A is equal to E because A and E are corresponding angles. A is equal to E. And we also very well understand that A plus B is equal to 180 degrees because that's a straight line. So this is a straight angle 180 degrees. A plus B is 180, but A is equal to E. So can I say E plus B is also 180? Right? So E plus B equals to 180 degrees. Likewise, C plus H equals to 180. How do we say that? See, C plus D is equal to 180 degrees. That's a very straightforward point. But D is equal to H. Where do we find D equals to H? Here. Because D and H are corresponding angles. So C plus H will become 180 degrees. Same is the case with A plus F and D plus G. So through the equality of various types of angles that we have seen here, it is very easy to understand why do interior angles on the same side and exterior angles on the same side make supplementary angles. Having learnt about the relationship between different angles when a set of parallel lines is cut by a transversal, let us now understand what a triangle is and what are its types. Now, triangle is a figure that is bounded by three straight lines. Any figure bounded by three straight lines can be taken as a triangle. Here, as you see, ABC is a triangle, right? It is formed by three straight lines, right? This is the first straight line, second straight line and the third straight line. Okay, so a figure bounded by three straight lines is called a triangle. Now, any triangle will have three sides, obvious, right? There will be three sides and three angles. What are the three sides here? AB can be taken as the first side, BC is the second side and AC is the third side. And likewise, there will be three angles: angle BAC, angle ABC and angle ACB. Alright, so let's give some names to each of these sides and each of the angles here. For example, let's say the side BC is equal to A. The length of the side BC is A, the length of the side AC is B, and the length of the side AB is equal to C here. Alright, so we can simply say side A, which is the length of the side B and side C. Likewise, there are three angles, right? This can be simply called as angle A, angle B and angle C here. Okay, now the very first point that we need to understand here is the sum of the interior angles. In any triangle, the sum of all the three angles, angle A plus angle B plus angle C, will be equal to 180 degrees, right? So A plus B plus C is equal to 180 degrees, right? Sum of all the three angles in a triangle will always be equal to 180 degrees. Now the second point here is with respect to the sides of a triangle, right? The point is the sum of any two sides of a triangle will always be greater than the third side. You take any two sides of any type of triangle, the sum of those two sides will be larger than the third side. For example, here A plus B will be greater than C, right? Length A plus length B will be greater than C. Likewise, B plus C will be greater than A, and A plus C will be greater than B. So the point is sum of the two sides of a triangle is greater than the third side. So we can say A plus B greater than C, and B plus C greater than A, and A plus C greater than B, right? Sum of the two sides is always greater than the third side. And in a similar way, the difference of the two sides is always lesser than the third side. If you take the difference of any two sides of a triangle, it will be lesser than the third side. So we can say A difference B will be less than C, B difference C will be less than A, and A difference C less than B, right? B difference C is B minus C or C minus B will be less than the third side. Likewise, A minus B or B minus A, the positive value there will be lesser than the third side C, and A difference C, which can be A minus C or C minus A, depending on what is greater there, the difference will be less than B. So the point here is sum of two sides is always larger than the third side, and the difference of two sides is smaller than the third side, right? Lesser than the third side. Now next comes the types of triangles, right? There can be different types of triangle based on, the relationship between angles or based on the sides here. So let's look at what are the different types of triangle. Now based on angles, there are three types of triangle, right? Based on angles, if you have to classify, we can say there are three triangles. The first one is a right angled triangle, right? A right angled triangle. Now what is a right angled triangle? We all know that right angle is 90 degrees, equal to 90 degrees. So a right angle triangle is the one which has got one of its angle as 90 degrees, right? So that's a special case. If one of the angles is 90 degrees, then it is called a right angle triangle. Remember, there can be only one angle that is equal to 90 degrees. A triangle cannot have two angles that are 90 degrees, because sum of the two angles is 180 degrees. Yes or no? Sum of the two angles is 180 degrees. So if one of the angles is 90, and if you say even the second angle is 90, then third angle will become 0. But angle here cannot be 0, right? So only one of the angles is 90 degrees. A triangle is right angle triangle. Then an acute angle triangle. What is an acute angle triangle? We know that an acute angle is less than 90 degrees. Angle less than 90 degrees is an acute angle. So if a triangle has got all the three angles less than 90 degrees, then it is called an acute angle triangle. And the third one here is obtuse angle triangle, right? Again, from the definition of obtuse angle, right? What is an obtuse angle? Angle between 90 degrees and 180 degrees. So if one of the angles is greater than 90 degrees, then that triangle is known as an obtuse angle triangle, right? So these are the this is the classification of triangle based on the angles here, right? Then there is another classification based on the sides. So let's look at that classification now based on the sides of the triangle, right? The first one here is scalene triangle, right? What is a scalene triangle? A triangle where all the three sides are different, right? The length of all the three sides are different. A is different from B, is different from C. Such a triangle is called a scalene triangle. All the three sides are different. Scalene triangle. Then we have an isosceles triangle, right? What is an isosceles triangle? The one where two sides are equal, right? In a triangle, if any of the two sides are equal, then that can be called as an isosceles triangle. For example, if A is equal to B, or B is equal to C, or C is equal to A. In all these three cases, the triangle becomes an isosceles triangle. So the two sides are equal, or the two angles are equal, right? It is obvious that when two of the sides are equal, the opposite angles will also be equal, right? So isosceles triangle is the one where where the two sides are equal or the two opposite angles are equal, right? Likewise, in scalene triangle, when we say that all the three sides are different, it is obvious that all the three angles would be equal, right? It is not possible that two of the angles are equal but still the triangle is a scalene triangle, right? If two of the angles are equal, means the two opposite sides are equal, and if two opposite sides are equal, the triangle becomes an isosceles triangle, right? And the last one here is an equilateral triangle. What is an equilateral triangle? The one which has got all the three sides equal. A is equal to B is equal to C. Such a triangle is called an equilateral triangle. And it's obvious that if the three sides are equal, then the three angles would also be equal. So in an equilateral triangle, we can say all the three sides are equal, or all the three angles are equal. Isosceles triangle, any two sides are equal or any two angles are equal, right? So if two sides are equal, the opposite angles would be equal, okay? And scalene triangle is the one where all the three sides are different or all the three angles are different. And then it's obvious that if the triangle is equilateral, we know all three angles are equal. Sum of the three angles is 180 degrees. So what will be each of the angles there? 60 degrees, because 60 plus 60 plus 60 makes it 180 degrees. So in an equilateral triangle, each of the angle will be equal to 60 degrees. Right? So that's about the classification of triangle based on the angles and sides there. Okay. Then there can be special cases here. For example, a right angled isosceles triangle. What is meant by a right angled isosceles triangle? A right angled triangle is the one where one of the angles is 90 degrees. Right? And isosceles triangle is the one where the two sides are equal, any two sides are equal. So a right angled isosceles triangle will have one angle as 90 degrees and the two sides which include that angle of 90 degrees will also be equal. So that's like a special case here, right angled isosceles triangle. Okay. Then generally right angled scalene triangle. So three sides would be different but one of the angles is 90 degrees and so on. So that's about the classification here. Now next comes another important point, which is about exterior angle. See, when any one of the sides of this triangle is produced, we get an exterior angle. For example, look at the side BC. What is the angle here? Angle C, right? This is C, angle C, let us say, the interior angle. But if the side BC is produced, what do we get? Let's say if the side BC is produced up to a particular point D, right? Or it is simply produced. Then we find that there is also an exterior angle that is formed. Let's say this is C dash. Okay, the vertex here is C, the point is C, interior angle generally referred as angle C, but the exterior angle, let's say it is called C dash. Now the point to be noted here is that this angle C dash will be equal to the sum of the other two angles. What are the other two angles? A and B here. Alright, so there are three angles, three interior angles, angle B, angle C and angle A, right? When any of the sides are produced, we get an exterior angle, and that exterior angle will be equal to the sum of the other two interior angles. And it's very easy to understand. So the point which I am trying to make here is C dash will be equal to A plus B. The angle C dash will be equal to A plus B. How do we prove this? It's very simple. A plus B plus C equals to 180 degrees. Alright. Now if you look at C plus C dash, what is C plus C dash? Angle C and angle C dash, that is the interior angle and the exterior angle, are making a straight line, which means C plus C dash is equal to 180 degrees. C plus C dash is 180. C plus C dash is equal to 180 degrees. Now if you take these two equations, what do we get? A plus B plus C equals to C plus C dash. C and C gets cancelled. We can say that C dash will be equal to A plus B. And same is the case with the other two vertices as well, right? If these sides are produced, let's say, the exterior angle A dash will be equal to angle B plus angle C. And the exterior angle B dash will be equal to angle A plus angle C. So this is another important point which you need to keep in mind, that an exterior angle at any one of the points of a triangle will be equal to the sum of the other two interior angles here. So that's about triangle, the various types of triangles based on angles and the sides here, and a few of its properties. Let us now learn about congruency and similarity of triangles. I shall explain this to you with the help of simple illustrations as shown on the board here, right? If you look at the left hand side, we have got two congruent triangles, right? The two triangles here are ABC and PQR, and on the right hand side are two similar triangles represented by ABC and PQR. So what exactly is meant by congruent triangles and similar triangles, and what is the difference between these two cases? Let's understand. Let's look at congruent triangles here. As we see, we have two triangles ABC and PQR. Now if you look at the two triangles, they appear to be same in shape, right? The two triangles are similar in shape and also in size. The point here is the angles of the triangle ABC will be equal to the corresponding angles of the triangle PQR, and also the sides of the triangle ABC will be equal to the corresponding sides of the triangle PQR. Such triangles are known as congruent triangles. They are exactly the same, not only in shape but also in size, right? The three angles are equal to the three corresponding angles of the second triangle, and the three sides are equal to the three corresponding sides of the second triangle. So congruent triangles are those which are perfectly same in shape as well as in size, which means if we superimpose one of the triangles on the other, they will coincide perfectly without any deviation. So two congruent triangles simply means same in shape and in size. So all the three angles are equal to the corresponding angles, and all the three sides are also equal to the corresponding sides. Now let's look at similar triangles. What do you see? Two triangles ABC and PQR. Now clearly, just through a glance, we see that the triangles are similar in shape. Yes, the two triangles are similar in shape, but not in size. So the basic difference between congruent triangles and similar triangles is that congruent triangles are similar in shape and in size, right? They have got the same shape and same size, whereas similar triangles have only got a similar shape, same shape, but not the same size. So if we clearly superimpose one of them on the other, we'll find that they will not be coinciding with each other. And what do we see here? I mean, the point to be noted is the three angles of the triangle ABC will be equal to the three corresponding angles of the triangle PQR, but the three sides of the triangle ABC will not be equal to the three corresponding sides of the triangle PQR. So the other difference here is, in congruent triangles, the three angles are equal to the three corresponding angles in the second triangle, and the three sides are equal to the three corresponding sides of the second triangle. But in similar triangles, the angles are equal in both the triangles, but the sides are not equal. But they are proportional, right? The sides are not equal, but they will be in proportion. So let's now see how do we check congruency of two triangles, or when do we say that the two triangles are congruent. Well, there are different ways of verifying this. The first one here is called SSS congruency, right? This is side congruency, which means if the three sides of the first triangle are equal to the three corresponding sides of the second triangle, then definitely the two triangles are congruent, and that is called the SSS congruency. The second one here is SAS congruency. Now what is this SAS congruency? This is side angle side congruency. Now what does it mean here? If any two sides of the triangle ABC and the angle included between them are equal to the corresponding two sides of the triangle PQR and the angle included between them, then also the two triangles are congruent. For example, if you take the sides AB and AC, right, and the angle between them, right, so this side, angle and side should be equal to the same corresponding sides and the corresponding angle. So side PQ, the angle between them, and the side PR. Then if these two are equal, we can say that the two angles are congruent. So this is known as the side angle side congruency. And the third one here is angle side angle congruency, which says if any two angles of the first triangle and one of its sides are equal to the corresponding two angles and the corresponding side of the second triangle, even then the two triangles are congruent. So we can take any two angles here, angle A and angle B, right, and one of the sides, let's say the side BC. Likewise, in the second triangle, the corresponding angles are angle P and angle Q, and the corresponding side is QR. So if angle A, angle B and BC are equal to P, Q and QR, the corresponding angles and the sides of the second triangle, then also the two triangles are called congruent, or the two triangles are exactly the same, right? So side, 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 which means all the three sides of the first one equal to all the three sides, corresponding sides of the second one. Side, angle, side, which means any two sides of the first one and the angle included by those two sides should be equal to the corresponding two sides of the second one and the angle included by those two sides. And angle side angle says any two angles of the first one and one of its sides should be equal to the two corresponding angles of the second one and the corresponding side. In all these three cases, we say that the two triangles are congruent. And as a special case, when we talk about a right angle triangle, let's say if you consider two right angle triangles, ABC and another right angle triangle PQR, right, PQR. Now the congruency of right angle triangle can be taken as the right angle, hypotenuse and its side, RHS, right. This is a special case, or we can consider it as a fourth case here, right. So obviously when there are two right angle triangles, the angles are right angle, right, the corresponding angles are right angle. So the right angle, the hypotenuse, their hypotenuse and the side, any one of the sides have to be equal. So right angle and right angle, which is for sure. The two hypotenuse have to be equal. So CP and RQ. And any one side, AB with PQ or AC with PR. If they are equal, then the two triangles are congruent. Which means again, if I put ABC on top of PQR, it will coincide perfectly without any deviation. So that's about congruency, right? Which talks about congruent triangles and the different ways of verifying congruency between two triangles. Let us now see about similar triangles. Well, we have already learned that similar triangles have same shape but they are different in size. Now, the point to be noted in case of similar triangles is, as I've already mentioned, the corresponding angles are equal. Angle A equal to angle P, angle B equal to angle Q, and angle C is equal to angle R. But the corresponding sides are not equal. Instead, they are in proportion. Now, what does it mean? If you look at the side AB is to PQ, this should be equal to BC is to QR, and this will be equal to AC by PR. So the point is, the ratio of the corresponding sides are equal. AB and the corresponding side PQ, that ratio will be equal to BC and the corresponding side QR ratio will be equal to AC and the corresponding side PR ratio. And this will be equal to the perimeter of the two triangles, right? The ratio of the perimeter of the two triangles. So perimeter of triangle ABC divided by perimeter of the triangle PQR. So the point to be noted here is that in case of similar triangles, the ratios of the corresponding sides will be equal to the ratios of the two perimeters of the two triangles. There is another equality that we see when it comes to similar triangles, and this is about the ratio of the squares of the corresponding sides, right? Like if we say AB square by PQ square equals to BC square by QR square equals to AC square by PR square. So the ratio of the corresponding sides, the ratio of the squares of the corresponding sides, and this will be equal to the ratio of the two areas. So area of triangle ABC upon area of the triangle PQR. So these are two important points about similar triangles. Point number one, the ratio of perimeters of the two triangles will be equal to the ratio of any two corresponding sides, AB by PQ or BC by QR or AC by PR. And point two is about the area, right? The ratio of the areas of the two triangles will be equal to the ratio of squares of any two corresponding sides. So AB square by PQ square or BC square by QR square or AC square by PR square. Also note that in case of similar triangles, the ratio of the areas of the two triangles is not only equal to the ratio of squares of any two corresponding sides, but it is also equal to the ratio of squares of any two corresponding altitudes or any two corresponding medians. Now we will learn about altitudes and medians in our next part of the discussion. So just make sure that you remember the point here, that is the ratio of the areas of two similar triangles is equal to the ratio of the squares of any two corresponding sides or any two corresponding altitudes or any two corresponding medians. And I'm sure once we learn about altitude and medians, you will be able to understand this point without any difficulty. Let us now learn about the different types of centers of a triangle. And the first one that we are going to look at is the centroid. Technically, centroid is the point where the entire mass of the triangle is concentrated. But in terms of geometry, we can say that centroid is the point of intersection of the three medians of a triangle, or it is the point where the three medians of the triangle meet. Now, what is meant by median? Median is a line that connects the vertex of a triangle with the midpoint of the opposite side, or a line that connects the midpoint of a side with the opposite vertex. Let us understand this with the help of a simple illustration. Now here we have a triangle ABC. As I've mentioned, median is a line that joins the vertex of the triangle with the midpoint of opposite side. So the opposite side here is BC. Let us assume that the midpoint of the side BC is D here. So the median would be AD, the line joining vertex with the midpoint of opposite side. So AD is one of the medians. One important point to be noted here is that every median will divide the triangle into two equal parts. So here the median AD has divided the triangle ABC into two equal parts. First triangle is ABD and the second one is ADC. And the area of each of these triangles is equal, right? The area of triangle ABD will be equal to the area of the triangle ADC, right? Likewise, we have two other medians which also divide the triangle into two parts, two equal parts, right? For example, if you look at the side AC, let us take the midpoint of the side AC as E. Right, the midpoint of side AC is E. So the line joining B to E will be the second median. Right, so this is the second median BE. Now BE again divides the triangle ABC into two parts. The first part is ABE and the second part is EBC. And the area of each of these parts is same. And the third median here would be the line joining the vertex C with the midpoint of AB. Let's assume the midpoint of AB is F. So the line joining C with F or F with C is the third median. And if you observe, all these three medians intersect at a common point, right? All these three medians are meeting at a common point, which is called the centroid of the triangle, denoted by G, right? The centroid is denoted by the letter G. Okay, so the centroid of the triangle G, as we see from this illustration here, is the point of intersection of all the three medians here. Okay, so median is a line joining a vertex of a triangle with the midpoint of opposite side. Median divides a triangle into two equal parts, and the point of intersection of the medians is the centroid. Remember that centroid is always within the triangle, right? It never lies outside the triangle. Centroid always falls inside the boundary of the triangle there. Now, one important and interesting fact here is that the centroid always divides the median in the ratio of 2:1, where two parts are on the vertex side and one part is on the base side. Centroid G here always divides any median in the ratio of 2:1, right? And two parts are on the vertex side, one part on the base side. For example, if you look at the median AD, right? If you see the points A, G and D are collinear. G lies between A and D. And G divides the line AD in the ratio of 2:1. Two parts on the vertex side. That means the distance from A to G is two parts and the distance from G to D is one part. So the ratio is 2:1. Alright, so we can say that AG by GD will be equal to 2 by 1. The ratio is 2 by 1. And not just for this median, right? Even the remaining two medians get divided by the centroid in the ratio of 2:1. So always remember 2 parts on the vertex side and 1 part on the base side. So if you look at the median BE, B to G is 2 parts and G to E will be 1 part. So we can say BG by GE is also 2:1. And similarly for the third median CF, we can say CG by GF. The ratio is always 2:1. So an important conclusion here is that centroid always divides the median into ratio of 2:1. Okay. Now another important conclusion or important point that we need to understand here is that if you look at the centroid G and the 3 vertices of the triangle ABC, we get 3 triangles within the original triangle, right? The first triangle here is ABG, right? The triangle ABG. The second triangle is ACG and the third triangle is BCG, right? So these 3 triangles, which are formed by 2 vertices of the original triangle and the centroid, together make the original triangle ABC here, right? So the first triangle ABG, second triangle ACG and the third triangle BCG, right? If we connect these 3 triangles, we get the original triangle ABC. And interestingly, the area of each of these smaller triangles is equal to 1/3 of the original triangle, right? So the second conclusion here is that area of triangle ABG is equal to the area of triangle BCG is equal to the area of the triangle ACG, right? ACG. The area of each of these triangles is equal to 1/3 of the area of original triangle ABC. The original triangle ABC, right? So for example, let's say the question says that the area of the triangle ABC is 48 square units, right? Area of the triangle ABC is 48 square units. Then what is the area of the triangle ACG, where G is the centroid? Now we know that area of triangle ACG will be 1/3 of the area of the total triangle or the complete triangle. So 1/3 of 48 square units, which is equal to 16, right? So we can say the area of the triangle ACG is 16 square units. And not only ACG, the area of BCG will also be 16 units and ABG will also be 16 square units. So that's again an important point on which questions can be asked in competitive exams, right? The point is the area of the triangle formed by 2 of the vertices and the center of the triangle will be equal to 1/3 of the area of the original triangle ABC. And now the third and a very important conclusion here. This is based on Apollonius theorem. The theorem here states that in a triangle ABC, if the median is AD, then we can say that AB squared plus AC squared will be 2 times of the median AD squared plus half of the third side, which can be taken as BD or DC. So let's say BD square, or this is equal to 2 times of AD square plus CD squared. So this is again an important conclusion which is based on the median of a triangle, right? This is based on a theorem which is known as Apollonius theorem, right? Named after the person who has derived this. It says that in a triangle ABC, where AD is the median, the sum of the squares of 2 sides, AB square plus AC square, right? These are the 2 sides, let's say AB square and AC square. So the sum of the squares of these 2 sides will be equal to 2 times the square of the median. The square of the median is AD square plus the square of half of the third side, right? We have already considered the 2 sides AB and AC. Now the third side here is BC. We have to take half of the third side. Now we very well know that the median is the line joining a vertex with the midpoint of opposite side. So D here is the midpoint. Now half of the third side can be taken as BD or DC, right? These two are equal. BD is equal to DC. So half of the third side can be taken as BD square, or it can be taken as CD square. So this is a theorem derived by a mathematician named Apollonius and named after him, which says if there is a triangle ABC with a median AD, then AB square plus AC square will be equal to 2 times of AD square plus BD square, or 2 times of AD square plus CD square. And not just for this median, we can take any of the medians here. For example, if you look at the median BE, then as per the theorem, the statement goes as follows, right? If you look at the triangle ABC with the median BE, then we'll say BA square plus BC square. Alright, BA square plus BC square will be equal to 2 times BE square plus half of the third side, which can be taken as AE square. So BA square plus BC square equals to 2 times of BE square plus AE square. And likewise for the third median, CF square, third median CF. How will the equation look like? We will say CA square plus CB square will be equal to 2 times of CF square plus AF square, or 2 times of CF square plus BF square. So that's a very important conclusion which we need to remember, so that if at all a question is asked on this theorem, it will be easy for us to arrive at the final answer. And the last point with respect to a median is as follows. If the given triangle ABC is equilateral, where all the 3 sides and the 3 angles are equal, then all the 3 medians would also be equal. Right? And if the triangle is an isosceles one, then only 2 of the medians would be equal. So this is again an important point which you need to remember, that in an equilateral triangle the 3 medians are equal, whereas in an isosceles triangle only 2 of the medians are equal in length. So that's about the first center of a triangle, that is centroid, which is the point of intersection of the medians of the triangle, and some of its properties as I've listed here. The next center that we are going to look at is the orthocentre of a triangle. Right? Orthocentre is the point of intersection of the altitudes of the triangle. Now what is an altitude? Altitude is a perpendicular drawn from a vertex of a triangle to the opposite side. Let us understand this with the help of a simple illustration here. Let's consider ABC as a triangle. ABC is a triangle here. Now, as I've mentioned earlier, orthocentre is the point of intersection of the 3 altitudes. And what is an altitude? Altitude is a perpendicular drawn from the vertex of the triangle to the opposite side. Right? So there will be 3 altitudes in a triangle, and all these 3 altitudes meet at a common point, which is called orthocentre. Now, what is a perpendicular? Perpendicular, we know that is the one which makes an angle of 90 degrees with the given side. So from point A, from the vertex A, if we draw a line such that it makes an angle of 90 degrees with the side BC, that will become the altitude of the triangle. Right? So let's say we drop a perpendicular here, right, such that the angle made here is 90 degrees. Now this perpendicular AD is the altitude. Likewise, from the vertex B, if we drop a line such that it makes an angle of 90 degrees with the opposite side, that is AC, then it becomes the second altitude. So let's say if we draw a line here such that the angle made by this line is 90 degrees with the opposite side, that's the second altitude. Let's consider that as BE. And the third altitude will be the one which is the line between C and the point where it meets BD, such BA, where it makes an angle of 90 degrees. So if we draw a line such that the angle here is 90 degrees, this is 90 degrees, let's say CF. CF is the third altitude. So these all these 3 altitudes, if you see, meet at a common point, right? And that point is known as orthocentre, which is generally denoted by the letter H, right? Orthocentre is denoted by the letter H here. So in simple words, orthocentre is the point of intersection of the 3 altitudes. An altitude is a line which is drawn from the vertex of a triangle to the opposite side such that it makes an angle of 90 degrees with the opposite side. Or in simple words, altitude is a perpendicular which is drawn from the vertex to the opposite side. So from the vertex to the opposite side, perpendicular, making an angle of 90 degrees. From the second vertex to the opposite side, making an angle of 90 degrees. And third vertex to the opposite side, making an angle of 90 degrees. So that's about orthocentre of a triangle. Now, based on the type of triangle, the position of orthocentre may change. For example, in an acute angle triangle, the orthocentre will be inside the triangle. But in case of an obtuse angle triangle, the orthocentre lies outside the triangle. Whereas in a right angle triangle, the orthocentre is at the vertex which has got the right angle. So this is something different in orthocentre when it is compared with median. Median, as you know, always lies within the triangle, inside the triangle. But orthocentre may lie inside, outside, or on the triangle based on the type of triangle there. So if the triangle is an acute angle triangle, acute angled triangle, then the orthocentre H lies inside the triangle, right? For obtuse angle triangle, if that is one of the angles is greater than 90 degrees, then the orthocentre H lies outside the triangle. And for a right angle triangle, right angle triangle, the orthocentre H lies at the vertex which has right angle, at the vertex of the right angle there. right? So if you consider ABC as a right angle triangle which has got the right angle at the vertex B, then the orthocenter is the vertex B here. So that's about the position of orthocenter based on the type of triangle there. Now one important conclusion that can be drawn with respect to the orthocenter of a triangle is that the angle made by any side with the orthocenter and the opposite angle are always supplementary. Let us understand this with the help of the illustration that we have taken here. For example, if you see the angle BHC, right? BC is the side. Now the angle made by the side BC with the orthocenter. Let's say this is theta, right? Angle made by the side BC with the orthocenter H. Okay, and the opposite angle. What is the opposite angle or the vertical angle? Is angle A. Now this angle BHC and angle A are supplementary. What does it mean by supplementary angles? They add up to 180 degrees, right? So we can say that angle BHC plus angle A is equal to 180 degrees. So the point here is the angle made by any side of the triangle with the orthocenter and the vertical angle or the opposite angle are supplementary. They add up to 180 degrees. Likewise, if you look at the side AC, the side AC makes some angle with orthocenter, right? It can be taken as angle AHC or angle CHA. So that angle AHC plus the other angle B will be equal to 180 degrees. And similarly for the third side there, angle ABH or AHB, right? Angle AHB plus angle C are also supplementary. So that's an important point which we need to remember. You need not remember these equations by heart. The point to be noted is angle made by a side with the orthocenter and the vertical angle are supplementary. So the question may be given as follows. It may say that in a triangle ABC the angle A is equal to 60 degrees. Then what is the angle BHC? Or what is the angle made by the side BC with the orthocenter? Now if this is 60 degrees, we know that this would be 120 degrees because 60 plus 120 will give us 180 degrees. So without doing any calculation, without solving the question, if you simply remember this point, you can mark the answer as 120 degrees. If A is 60, then angle BHC will be 120 degrees. So that's about the orthocenter and its properties. Let us now learn about the circumcenter of a triangle. Circumcenter is the point of intersection of the perpendicular bisectors of the sides of the triangle. Now, what is meant by a perpendicular bisector? It is a line that is perpendicular to the side of the triangle and bisects it. Right? What is meant by bisects here? It divides the side into two equal parts. So a line that is perpendicular to the side of the triangle and it divides the side into two equal parts is known as the perpendicular bisector. So we can draw three perpendicular bisectors, one for each of the sides, and the point of intersection of all these three perpendicular bisectors becomes the circumcenter of the triangle. Let's understand this with the help of an illustration. So triangle ABC as usual here. Let us draw the perpendicular bisectors for each of the sides here. If you look at the side BC, we know that perpendicular bisector bisects the side. That means it divides the side into two equal parts. So let's say this is the point where it bisects, right? This is the midpoint of the side and it is perpendicular to the side. So it is perpendicular means it makes an angle of 90 degrees. So this is one of the perpendicular bisectors. Likewise for the remaining two sides also we can draw perpendicular bisectors. Let's draw for side AC, right? Let's say this is the midpoint. That is, this is the point where the perpendicular bisects passes through. Now let's draw a line which is perpendicular. So the angle here is 90 degrees. And the third perpendicular bisector here for the side AB, right? It may be taken as shown here. So the angle made here is 90 degrees. Right? So you see here that all the three perpendicular bisectors meet at a common point, which is the circumcenter of the triangle. Circumcenter is generally denoted by S, right? So circumcenter S of the triangle is the point of intersection of all the three perpendicular bisectors for the sides of the triangle. Now the interesting fact about circumcenter here is that the circumcenter is equidistant from all the three vertices. The circumcenter S is equidistant from A, B and C, which means the distance from A to S is equal to the distance from B to S is equal to the distance from C to S. And it is because of this reason that from this point, keeping it as a center of a circle, we can draw a circle which passes through all the three vertices, right? This can be considered as the center of a circle that circumscribes the triangle. What is meant by circumscribing the triangle? It passes through the 3 vertices of the triangle. And why does this happen? Because this is equidistant from all these 3 points. So it is obvious that all the 3 points lie on a single circle, and there is only one circumcircle that can be drawn for a triangle. So this is the center of a circle which passes through all the 3 vertices. So I'm just trying to draw a circle here. Let's say this is the circle. May not look like a circle, but let's understand the point there, right? So S is the center of a circle which passes through all 3 vertices, and this is known as the circle which circumscribes the triangle. The triangle is completely inside the circle and all its 3 vertices lie on the circle there. So that's about circumcenter, the point of intersection of the perpendicular bisectors of the sides. Now, what is circumradius? Circumradius is the distance from the vertex of the triangle to the circumcenter, right? This can be taken as radius. This is the center of the triangle. So center of the triangle to any of the vertex is known as circumradius, which is denoted by capital R. Likewise, SC is also the circumradius, and SB is the circumradius. Okay, so we can say that the circumradius R is equal to the distance between the circumcenter and the vertex, so which can be taken as AS or BS or CS. All these 3 would be equal there. Now, another important property with respect to circumcenter is that the angle made by any side with the circumcenter will be 2 times the angle of the opposite vertex, right? Like in case of orthocenter, we have seen that the angle made by any side with the orthocenter and the opposite angle are supplementary. But in case of circumcenter, the angle made by any side with the circumcenter is twice the opposite angle, which is angle A in this case. So if we say angle BSC, right, the angle made by the side BC with the circumcenter will be 2 times the angle A. Likewise, the angle CSA will be equal to 2 times the opposite angle, opposite vertical angle, right, which is angle B here, 2 times angle B, and the angle ASB will be equal to 2 times the angle C here. Now this is actually based on the properties of circle and a chord, right? You very well understand that the chord of a circle makes an angle theta at the center of the circle, and the angle made by the same chord on the other arc will be half of the angle made at the center of the circle. So based on that property, we can conclude this for the circumcenter. So the angle made, this is like a chord. If you observe, BC is the chord for the circle, right? So the angle made by this chord at the center of the circle will be 2 times the angle made on the opposite arc, any point on the opposite arc. A can be taken as one of those points. So this is an important result which we need to remember, so that if a question is asked based on this, we can mark the answer without doing any calculations, right? For example, you know, the question may say that the angle A is equal to 30 degrees. The angle A is 30 degrees. Then what is the angle made by the side BC with the circumcenter? If this is 30, this should be 2 times of 30. It will be 60 degrees, right? So an important property for circumcenter. And the next point here is about the position of circumcenter, right? The position of circumcenter changes based on the type of triangle, like we have seen in case of orthocenter. Now if the triangle is acute angle, then the circumcenter lies inside the triangle, right? If it is obtuse angle, then the circumcenter lies outside the triangle. And for a right angle triangle, the circumcenter S is the midpoint of hypotenuse. So let's understand, let's just put it on paper here quickly. For an acute angle triangle, the circumcenter S lies inside. For obtuse angle triangle, the circumcenter S lies outside the triangle, same as the orthocenter there. But for a right angle triangle, which is a special case here, right angled triangle, the circumcenter is the midpoint of hypotenuse. So it actually lies on the triangle and it is the midpoint of hypotenuse. Midpoint of the hypotenuse. Right? So if we consider a right angle triangle, let's say this is the right angle triangle. A, B, C. Right? Right angle triangle, angle at A is 90 degrees, right? Right angle triangle. So what will be the circumcenter? It will be the midpoint of BC. Circumcenter S will be on this one. If it is equilateral or if it is acute angle, the circumcenter will be inside. Obtuse angle, the circumcenter will be outside. Now again, the point to be noted here is, if this is a circumcenter, we can draw a circle which passes through the 3 vertices A, B, C with the center as S. Now if you want to find out the circumradius, what is the circumradius? The distance of the circumcenter from the vertex there. So SB can be taken as a circumradius R, or SC can also be taken as a circumradius, or SA. Right? But the interesting point here is, in case of a right angle triangle, since the circumcenter is the midpoint of hypotenuse, we can say that the circumradius R will be half of hypotenuse. Right? So that's again a special case here. For a right angle triangle, the circumradius R is half of the hypotenuse. So if the length of the hypotenuse, let's say, is 5 units, circumradius will be 2.5 units. If the length of the hypotenuse is let's say 13 units, then the circumradius R will be 6.5 units, and so on, since it is the midpoint of the hypotenuse. Okay, so let's also make a note of that. R for a right angled triangle, R is equal to half of hypotenuse. And also there is a special case of equilateral triangle. For an equilateral triangle where all the 3 sides are equal, the circumradius R will be equal to A by root 3. A by root 3 units, where A is the side of the triangle there, right? Equilateral triangle is the one where all the 3 sides are equal. So for an equilateral triangle, the circumradius R is equal to A by root 3, where A is the side of the triangle. So that's about circumcenter and its various properties. And let us now learn about the incenter of a triangle. Incenter is the point of intersection of the angle bisectors of the interior angles of the triangle. Now what is meant by an angle bisector? Well, angle bisector is a line that divides the interior angle into 2 equal parts, or 2 equal angles, right? Now there can be 2 types of angle bisectors, interior angle bisectors or exterior angle bisectors. Both of them have the same feature, right? An angle bisector, interior or exterior, divides the angle into 2 equal parts or 2 equal angles. So since there are 3 angles in a triangle, 3 interior angles in a triangle, we have 3 angle bisectors, and all these 3 angle bisectors meet at a point which is known as the incenter of the triangle. Let us understand this with the help of a simple illustration. So ABC is a triangle. Now there are 3 interior angles here, angle A, angle B and angle C. Now as we know, angle bisector is the one that divides the angle into 2 parts. So if we draw a line from the vertex B such that the angle B gets divided into 2 parts, right? So this is the angle bisector, let's say, right? So angle here is B by 2 and the angle here is also B by 2. B by 2 plus B by 2 will give the complete angle B here. So simply angle bisector is a line that divides the angle into 2 equal parts or 2 equal angles. So each angle becomes half on each of the sides there. Now before we move on and draw the other angle bisectors and see what an incenter is, let us understand an important property of an angle bisector. If we extend the angle bisector of angle B here such that it meets the opposite side at point E, right? So BE is the angle bisector for angle E here. Now the important point to be noted here is this angle bisector has divided the opposite side AC in a particular ratio, right? That ratio in which it divides the opposite side is equal to the ratio of the sides that contain the angle B. Let us understand this with the help of the sides here. Now if you observe, BE is the angle bisector which divides the side AC in a particular ratio, right? So we can say the ratio in which the sides are divided, AE by EC. This ratio will be equal to the ratio of the sides which contain the angle. Now what sides contain this angle? AB and BC. So we can say this will be equal to AB by BC. Likewise, even for the other angle bisectors, when we extend them so that they divide the opposite side in some ratio, that ratio in which the opposite side gets divided will be equal to the ratio of the sides that contain the particular angle there, right? Now let us draw the other angle bisectors. For example, for angle A, the angle bisector is this, let's say. So this will be A by 2, the other part is also A by 2. It meets the opposite side at D. Now again, going by the first point here, we can say BD by DC, the ratio in which the side has got divided, BD by DC will be equal to the ratio of the sides which contains the angle A. So what sides contain the angle A? AB and AC. So this can be taken as AB by AC. And same goes for the third angle bisector. So if we draw an angle bisector here, right, it will meet at some point in the opposite side. However, the point of intersection of all these 3 angle bisectors is known as the incenter, which is denoted by the letter I. So incenter is denoted by the letter I. Okay. So what we have learned here so far, that the incenter is the point of intersection of angle bisector. An angle bisector divides the angle into 2 equal parts. And when we extend the angle bisector, it divides the opposite side in a ratio which is equal to the ratio of the sides that contain the particular angle there. So the intersection gives us the Incentre, which is denoted by I. Now what is special about this Incentre I here? The point is, this Incentre I is equidistant from all the three sides. If we draw a perpendicular from the Incentre to each of the three sides, the perpendicular length will be equal for all three of them, right? For example, let's say IE is the perpendicular drawn here, angle is 90 degrees, right? Likewise, ID is another perpendicular, and if you draw one more perpendicular, let's say IF, right, 90 degrees. So the distance of the Incentre from all the three sides will be equal. IF will be equal to IE will be equal to ID. And by considering this distance as the radius, right, if we draw a circle, we find that the circle will touch all the three sides internally, and that circle is known as incircle. So I is the center of a circle which touches all the three sides, right? So let me just draw a circle here, an approximate circle, right? So this is known as the incircle, right? The circle here is called incircle. Incircle, and the radius, what is the radius? IE or ID or IF is known as in radius, which is denoted by the small letter r, right? So if you compare Incentre with Circumcentre, what do we see? Circumcentre is the center of a circle which passes through all the three vertices, or it circumscribes the triangle, whereas Incentre is the center of a circle which touches all the three sides, or it is completely inscribed within the triangle. And circumradius is the distance of the circumcentre from any of the vertex, which is denoted by capital R, whereas in radius is the distance of the incentre from the three sides. So if you draw a perpendicular, we will get the distance there, and all those three are equal. That is the reason we are able to draw a circle which touches all these three sides, and this in radius is denoted by the small letter r. Now, like in case of circumcentre and orthocentre, we have seen that the position changes based on the type of triangle, right? Like orthocentre and circumcentre both lie outside if it is an obtuse angle triangle. Both of them lie inside if it is an acute angle triangle. And for a right angle triangle, orthocentre is the vertex which contains right angle, and circumcentre is the midpoint of the hypotenuse. But incentre always lies inside the triangle, right? Whatever be the type of triangle, equilateral or scalene or right angle, obtuse angle or acute angle, the incentre is always inside the triangle, because with the help of incentre we draw a circle which has to touch all the three sides internally. So obviously it has to fall inside the triangle, whatever be the type of triangle be. So that's about incentre, which is the point of intersection of the internal angle bisectors. And an important point here which I would like to repeat is that angle bisector always divides the opposite side in a ratio which is equal to the ratio of the sides that contain the particular angle there. Okay. Now the next point to be noted here is that the angle made by any of the sides with the incentre will be equal to 90 degrees plus half of the opposite angle. Now we have been discussing about such properties for each type of center. So the property here for incentre is that the angle made by any side with the incentre will be equal to 90 degrees plus half of the opposite vertical angle, right? So for example, if you look at the angle BIC, this angle, right, angle BIC will be equal to 90 degrees plus the angle A, right? So that's again an important conclusion which you need to remember. Angle BIC is equal to 90 degrees plus angle A. Likewise, if you say side AC, the angle made by side AC with incentre is AIC. So angle AIC will be this is 90 degrees plus half of the angle. 90 degrees plus half of the angle. So this will be 90 degrees plus half of the opposite angle. What is half of the opposite angle? Angle B by 2. And the third side here, AB, the angle made by side AB with incentre is AIB. So angle AIB will again be 90 degrees plus the opposite angle is C. So half of that opposite angle C by 2. So this is again a very important point which we need to remember, so that questions based on this can be answered without any difficulty in about 2 to 3 seconds, right? For example, let's say the angle A is equal to 60 degrees. Angle A is 60 degrees. Then the question says, what is the angle made by the opposite side with the incentre? We know that the angle made by the opposite side with the incentre is 90 degrees plus half of 60 degrees. Half of 60 is 30. So 90 plus 30, which is 120 degrees. Likewise, the question is that angle made at the vertex A is 30 degrees. This is 30 degrees. This angle is 30 degrees. So what will be BIC? 90 degrees plus half of 30 is 15 degrees. 90 plus 30, 90 plus half of 30, which is 15. 90 plus 15 equals to 105 degrees, right? So this is how this particular conclusion here will help us answer some of the questions based on Incentre without any difficulty. Okay, and now let us look at the in radius, right? That is the radius of in circle for an equilateral triangle. In the previous case, that is for circumcentre, we have seen that for an equilateral triangle, the circumradius is a by root 3, and for an equilateral triangle, the in radius is a by 2 root 3. So if the triangle is equilateral, for equilateral triangle, the in radius r will be equals to a by 2 root 3, where a is the side of the equilateral triangle, right? Basically what happens is the in radius for an equilateral triangle is half of circumradius. See, we have already seen that circumradius r equals to a by root 3. Circumradius r is a by root 3 for an equilateral triangle, but for an equilateral triangle r is equal small r, that is in radius is equal to circumradius by 2. So a by root 3 by 2 will give us a by 2 root 3, right? So this is again an important conclusion which you need to remember, that is for an equilateral triangle the in radius is a by 2 root 3, where a is the side of the equilateral triangle. Now before we move on to the next part of this session, let me also explain you another special property which holds for the angle bisectors, right? Here we have seen that Incentre is the point of intersection of the interior angle bisectors. But let's say if we take exterior angle bisectors, for example, if we extend the side AC, right? If we extend the side AC, what do we see? There is an external angle here, right? The external angle here. Okay, interior angle is C, the exterior angle is, let's say, C dash. So if this is the vertex C, let's say this angle is C and this angle is C dash. Now the point to be noted here is that C dash, the angle C dash here will be equal to the sum of the other two angles, right? This is for an exterior angle. Angle C dash will be equal to the sum of the other two angles. How do we come to this conclusion? See, if you look at the complete angle here, this is a straight angle. Angle C plus angle C dash should be equal to 180 degrees because it's a straight line. Now we know that in a triangle, sum of all the three angles is 180. So we can say that angle A plus angle B plus angle C equals to 180 degrees. Also, if we extend this line, we know that angle C plus angle C dash, angle C plus angle C dash is also equal to 180 degrees. From these two statements, it is clear that angle C dash here is equal to angle A plus angle B. So for any exterior angle, it will be equal to the sum of the other two angles. For example, if we extend this line now, we get an exterior angle B dash. B dash will be equal to angle A plus angle C. Likewise, if this is extended to get the exterior angle A dash, angle A dash will be equal to angle B plus angle C. So that's one important point which you need to remember. That is, the exterior angle at any vertex of a triangle is equal to the sum of the other two interior angles. And the second point here is, if we draw angle bisectors for the exterior angle. Now angle bisector for interior or exterior means the same. It will divide the angle into two parts. So let's say we draw an angle bisector which divides this angle into two parts, right? So this is C dash by 2, this also is C dash by 2. Likewise for the side B, we have some exterior angle. Let's say this is angle B dash. This is the vertex B here, right? Now if you draw an exterior angle bisector, right? Let's say they meet at a point P. Right. Now the second conclusion which I was talking about is as follows. Now we have seen that the exterior angle bisectors for B and C have met at a point P. They intersect at a point P. Now the angle made by the side BC with this point P will be equal to 90 degrees minus half of the other angle, which is similar to what we have seen here. In this case, angle made by the side BC with the Incentre is equal to 90 degrees plus half of other angle. But if we take exterior angle bisectors, then the angle made by the side BC with the point of intersection of exterior angle bisectors will be equal to 90 degrees minus half of the other angle there. So the conclusion that we can make here is angle BPC, right? BPC will be equal to 90 degrees minus half of the angle, which is the opposite angle, right? Half of opposite angle. So half of A by 2. So that's again an important conclusion which you need to follow. Likewise, let's say if we get the point of intersection of exterior angle bisectors for A and C, then the angle made by APC, if the point of intersection is P, angle APC will be equal to 90 degrees minus half of angle B. And same goes for the next side as well. If we draw the exterior angle bisectors which meet at a point P, then angle BPA or APB will be equal to 90 degrees minus half of angle C. So that's one special point which comes for angle bisectors, right? Basically related to exterior angle bisectors, right? So that's about Incentre and its various properties. So make sure that you remember about all these different types of centers and their properties properly, so that it becomes easy for us to answer the questions based on any of these properties. Now that we have learnt about the different centers of a triangle, which include centroid, orthocentre, circumcentre and the incentre, let us look at a few properties related to these different centers. Now point number one here is that in an equilateral triangle, where all the three sides and the three angles are equal, the orthocentre, circumcentre and the incentre, all these 3 points coincide with the centroid G, right? In an equilateral triangle, H, that is the orthocentre, S, circumcentre and I, incentre, coincide with the centroid G. So clearly, if the triangle is equilateral, all the 4 points would be existing at the same point, which is nothing but the centroid of the triangle there, right? So that is point number one. Now point 2 here is about a non-equilateral triangle. What happens in case of a non-equilateral triangle? Let's look at it. Here it says in a non-equilateral triangle, H, that is the orthocentre, G, centroid and S, the circumcentre, are all collinear. Now what does it mean when we say the points are collinear? It means that they lie on the straight line. So the point here is, in any non-equilateral triangle where the sides and angles, all the sides and all the angles are not equal, in such a case the orthocentre, centroid and the circumcentre are collinear. They lie on a straight line which is known as Euler's line. So Euler's line is a line which passes through the orthocentre, centroid and the circumcentre of a triangle, of a non-equilateral triangle. Let's understand this with the help of a simple illustration here. Now as you see, ABC is a triangle and clearly this does not look to be an equilateral triangle. So clearly these 3 points will not be coinciding, right? They'll be at different positions. Now we know that in a non-equilateral triangle, these 3 lie on a straight line. They are collinear. So if we try to mark the orthocentre, let's say this is the orthocentre H and the centroid G and the circumcentre S, we will see that all these 3 points pass through a straight line, right? And this line here is known as Euler's line, right? Euler's line, named after the mathematician who had derived this point there. Okay, so these 3 points lie on the same straight line. I would like to draw your attention to a point here, that the incentre I may or may not be on the Euler's line, right? These 3 points will always be on the Euler's line, but incentre need not be on the Euler's line always. Only in case of an isosceles triangle we see that incentre also lies on Euler's line, but otherwise it does not. However, this point would not be so useful while solving the questions in the exam, but what would be actually useful is the relationship between the orthocentre, the centroid and the circumcentre when they lie on the Euler's line. The point here is circumcentre G divides the line joining H and S, that is the orthocentre and the circumcentre, in the ratio of 2:1. That means if this is 2 parts, then this would be 1 part, that is HG is to GS will be in the ratio of 2:1. So we can say HG, that is the distance between orthocentre and centroid, by GS, centroid and circumcentre, will be in the ratio of 2:1. So that's one important property which we need to remember with respect to non-equilateral triangles. Let us now look at a few very important properties based on a right angle triangle, and we shall do this with the help of an illustration as shown here. So what we see here is a right angle triangle ABC which has the right angle at the vertex B, right? Now here the side BC is known as the base of the triangle, AB is the perpendicular side of the triangle and AC is the hypotenuse. And we very well know that hypotenuse is the largest side in a right angle triangle. What is the reason? The point here is angle B is 90 degrees, right? In this triangle here, angle B is 90 degrees, which is the largest angle, right? The remaining 2 angles, angle A and angle C, would be less than 90 degrees. Now, in any type of triangle, the side which is opposite to the largest angle is the largest side, and the side which is opposite to the smallest angle is the smallest side. Now since in this triangle angle B is largest, the side opposite to angle B, that is AC or the hypotenuse, is the largest side, and the side opposite to the smallest angle would be the smallest side. Not just for a right angle triangle, any type of triangle, always the side opposite to the largest angle is largest side, and the one which is opposite to the smallest angle is the smallest side. So clearly in a right angle triangle the hypotenuse would be the largest side. Now let us look at the properties here, right? The first and the foremost is Pythagoras theorem, right, which is one of the fundamental concepts in geometry, right? As far as Pythagoras theorem is concerned, it states that the hypotenuse square will be equal to the sum of the squares of the remaining two sides. So in this triangle ABC here, we get that AC square, hypotenuse AC square will be equal to the sum of the squares of remaining two sides, that is AB squared plus BC squared. AB squared plus BC square. This is the Pythagoras theorem, which is one of the most important fundamental concepts or pillars of geometry, right? So AC square, that is hypotenuse square, equals to AB square, perpendicular square, plus BC square, the base square, right? So holds true for a right angle triangle. Now there are various other properties based on a right angle triangle which can be derived by considering a perpendicular from the vertex B on the opposite side AC. So let us draw a perpendicular from point B to the opposite side AC. So let's say the perpendicular here is as shown, right, which meets the side AC at the point D, and this angle here is 90 degrees, right, perpendicular, it is perpendicular, so these two lines intersect at 90 degrees. Now based on this perpendicular BD here, which is on the hypotenuse AC, we can come to a lot of conclusions, right? I'll just list down all those conclusions here without looking at the proofs, because examination point of view, if we can remember the identity or the formula, that should be sufficient for us to arrive at the required answer, right? Even if you do not know what the proof is, doesn't really matter. So let us look at all these identities based on the perpendicular that we have drawn here. Now the first one would be BD square, right? The perpendicular BD square in a right angle triangle will be equal to AD into DC. AD into DC. Then next comes AB square. AB square, right? The side AB square can be taken as AC into AD. And next one here is BC square, right? BC square can be taken as AC into DC, right? So these are a few of the important identities based on a right angle triangle, and let me tell you, all these are derived using the concept of similarity. If you observe, when we draw a perpendicular from the vertex B to the opposite side AC, we get two triangles within the larger triangle, right? So the original triangle here is ABC, but after drawing this perpendicular we have got two smaller triangles. The first one is ABD and the second one is BDC. And when we look at the properties of similarity, we'll find that these two triangles are similar, right? These two triangles here are similar triangles, and based on concepts of similarity, we can derive these points here. The first one is BD square equals to AD into DC. Then second one says AB square will be equal to AC into AD, and the third one is BC squared will be equal to AC into DC. Now I'll derive one of these for you, and similarly you can derive the other two there. Now the point to be noted here is, as I've mentioned, the two triangles ABD and BDC are similar triangles. Now if we try to go by similarity, we see that angle D in both the cases is 90 degrees, right? Angle ADB is 90 degrees and BDC also is 90 degrees. The reason here is this is a straight line and the straight angle is 180. So this side 90 degrees and the other side is also 90 degrees. Now let us assume that this angle C here is theta, right? Angle C is theta. Then what will be angle B in this triangle BDC? Let us draw two separate triangles to understand this clearly. Let us say one of the triangle is ABD, right? A, or let's say A, D and B, and the second triangle is BDC. The second triangle here is BDC, B, D and C. Now if you look at this triangle ABD, which we have taken here, ABD, angle D is 90 degrees. This is 90 degrees. Let us assume that angle C here is theta, right? So angle C in this case would be theta. Okay, and here angle D is also 90 degrees, right? In the triangle BDC, angle D is 90. So 90 degrees, angle C is theta. Now if you consider this triangle BDC, this is 90 degrees and angle C is theta, so angle B has to be 90 minus theta, right? Sum of all the angles has to be 180 degrees. So 90 plus theta and 90 minus theta. If we add all these values, plus theta and minus theta gets cancelled. So we will be left with 90 plus 90, that is 180 degrees. So this can be taken as 90 degrees minus theta. Alright, now angle B is 90 degrees minus theta. Angle B again not in the actual triangle, angle B in the triangle BDC here. Okay, now what about this angle here? You look at ADB, right? In triangle ADB, we know that this part of the angle we have taken as 90 degrees minus theta. This is 90 minus theta, this part has to be theta, because 90 minus theta plus theta will give us 90 degrees, right? So angle B in the triangle BDA, right, in the triangle BDA will be 90 minus theta, sorry, will be equal to theta. Getting the point? 90 minus theta is this in BDC. If this is 90 minus theta, the angle has to be 90 degrees, theta, because 90 minus theta plus theta will give us the complete angle as 90 degrees. Okay, so this is 90 degrees, angle B is theta. And now look at the remaining angles, that is angle A here. This is 90 and this is theta. Angle A has to be 90 degrees minus theta, because sum of all the angles has to be 180 degrees. So this is 90 degrees minus theta. Alright, now don't get confused here. This angle B and this angle B are two different angles, right? This is the part of BDC and this angle B here is the part of BAD. Now if you observe, these two triangles are similar because all the three angles are equal. One angle is 90 degrees here, here it is 90, theta and theta, 90 minus theta and 90 minus theta. We know that in two similar triangles all the three angles are equal and the corresponding sides are proportional, right? The corresponding sides are not equal, only the corresponding angles are equal, but the corresponding sides are proportional, which means the ratio of side BD by BC should be equal to the ratio of side AB by BC, should be equal to the ratio of sides AD by BD. So going by that concept of proportionality, what do we get? DB or BD, right, this side BD by the side DC should be equal to AD by the corresponding side BD should be equal to the hypotenuse here, right, AB by the hypotenuse BC. What is the logic here? We know that in two similar triangles the corresponding sides are proportional. So the corresponding bases BD by DC should be equal to the ratio of the corresponding perpendicular sides AD by BD should be equal to the ratio of hypotenuse AB by BC, right? So this is what we have derived from the two similar triangles. Now you look at these identities. We want to prove BD square equals to AD into DC. Use any two of these fractions here and we'll find that BD square will be equal to AD into DC. For example, look at this first two fractions, right? What do we see here in the first two fractions? BD by DC equals to AD by BD. Now cross multiply, what do we get? When we cross multiply BD into BD, that is BD square equals to AD into DC, right? So BD square equals to AD into DC. So this is how we can prove these equations here based on the concept of similarity. And the last property here based on a right angle triangle is as follows: 1 by BD square will be equal to 1 by AP square plus 1 by BC square, right? BD is the perpendicular that we have brought here. So 1 by BD square will be equal to 1 by AB square plus 1 by BC square. This is another important property based on a right angle triangle. So these are few of the properties for a right angle triangle which we need to remember, and this will help us a lot while answering questions from geometry, right? And as I've mentioned, you need not worry about the proof of each of these properties here. If you can remember them by heart, that should be sufficient, right? So the first one is Pythagoras theorem, which says hypotenuse square equals to the sum of the squares of the remaining two sides. Second one, based on a perpendicular from the right angle to the opposite side or on the hypotenuse, we get BD square equals to AD into DC. Now let us also understand how to remember these identities, right, without getting confused here. See what happens. If you look at the side BD, right, the side BD is a part of two triangles. Which are those two triangles? The triangle ABD and the triangle BDC. Now we are looking at BD square, right? BD square. If you observe, all the right hand sides are based on the hypotenuse. AD and DC. AD and DC part of hypotenuse, right? AC and AD. AC is the hypotenuse, AD is the part of hypotenuse. And look at this right hand side here, AC into DC. AC is the hypotenuse and DC also part of hypotenuse. So clearly all the right hand sides are based on either the hypotenuse or the parts of hypotenuse. But how do we decide which has to be considered for the given identities here? Look at this. The first one, BD square. We are looking at BD. Now BD is a part of two triangles. Triangle ABD and triangle BDC. Right? So in triangle ABD, what is the part of hypotenuse? AD. And the second triangle, what is the part of hypotenuse? DC. So AD into DC. Look at the second one, AB square. AB. Now if you look at this side AB, this also is a part of two triangles. The original triangle ABC and the upper part of the triangle ABD. Now let's take both the hypotenuse here. So in the original triangle, the hypotenuse is AC, so that AC. In the second triangle ABD, right? Why are we taking this triangle ABD? Because AB is a part of this triangle as well. Now in this triangle ABD, we get the part of hypotenuse as AD. Likewise the third one, BC square, right? Now look at BC, the base BC here. BC is a part of two triangles. What are those two triangles? The original triangle ABC and the bottom triangle BCD. Now consider the hypotenuse and its part, corresponding part. So the original hypotenuse AC, because BC is a part of the original triangle, so we get AC into DC. Why do we take DC? Because in the second triangle BCD, the part of hypotenuse is DC, so that DC comes here. So it's very easy to remember, right? Just consider the side that you're taking, either the perpendicular that you have dropped or the base or the perpendicular side, original perpendicular side. And on the right hand side we get hypotenuse multiplied by part, or the product of both the parts based on which side we have considered. Okay, so remember all these important points based on right angle triangle, so that answering the questions exam becomes easy for us. As per the Pythagoras theorem, we know that in a right angled triangle, AC squared will be equal to AB square plus BC square. That is, the hypotenuse square will be equal to the sum of the squares of the remaining two sides. But let us now derive similar relationships for an acute angle triangle and a obtuse angle triangle here. So as you see, the first triangle ABC is an acute angle triangle, right? The angle B here is acute. It is clearly less than 90 degrees. It is not a right angle. It is lesser than the right angle. So we can say angle B is acute angle now, and also the remaining two angles are acute. So since all the three angles are acute, this can be considered as an acute angle triangle. And look at the second triangle here, ABC. Clearly angle B is greater than the right angle, right? It is more than 90 degrees. So angle B is obtuse, and hence the triangle becomes an obtuse angle triangle. So here angle B is obtuse angle. Now what happens in case of an acute angle triangle and an obtuse angle triangle? In a right angle triangle, we know that AC square equals to AB square plus BC square. That is, AC square, the hypotenuse square, will be equal to the sum of the squares of the remaining two sides. Now let us derive similar relationships for these two triangles. We have clearly understood that the side which is opposite to the largest angle will be largest side, and the side which is opposite to the smallest angle will be the smallest side. Now if the angle is 90 degrees, if angle B is exactly 90 degrees, what do we get? The opposite side, AC square equals to AB square plus BC square. But here the angle is less than 90 degrees, which means AC square should be less than AB square plus BC square. Likewise in this case, the angle B is greater than 90 degrees. If it is exactly 90 degrees, what do we get? AC square equals to AB square plus BC square. But since the angle here is more than 90, the side also will be greater than what we have in a right angle triangle. Right? In a right angle triangle, AC square can be expressed as AB square plus BC square. But here it will be AB square plus BC square plus a little more than that. Right? It should be more than AB square plus BC square. So let us derive those two relationships here. What we are going to do in the first case is drop a perpendicular from the vertex A on the opposite side, right? Let us drop a perpendicular. So let's say AD is the perpendicular here. It meets BC at the point D. So angle D here is 90 degrees. Now if you observe, ABC has got two right angle triangles. The first one is ADC, right? The first one is ADC. The second one here is ADB, right? There are two right angle triangles. Now let us look at the triangle ADC, right? In triangle ADC, what do we see? AC squared, right? This is a right angle triangle. So AC square will be equal to AD square plus DC square. AD square plus DC square, right? Now if you observe this side DC, right? The side DC here can be taken as BC minus BD. DC is nothing but the complete side BC, the complete base BC minus BD. So let us substitute that. So we get AC squared equals to AD square plus DC can be expressed as BC minus BD whole square. Let us now apply A minus B whole square expansion and see what do we get. So we get AD squared plus this is BC squared plus BD squared minus 2BC into BD. Now if you look at the other part of the triangle here, the other right angle triangle, what is it? ADB, right? In the triangle ADB, we know that AB squared will be equal to AD square plus BD square. Yes or no? This is from the triangle ADB. In the triangle ADB, the hypotenuse is AB. So AB square can be taken as BD square plus AD square. And look at this relationship here. We have AD square plus BC square plus BD square minus 2BC into BD. Now here AD squared plus BD squared. AD square plus BD square can be replaced with AB square. Right? So what do we get? Finally AC square will be equal to AD square plus BD square is equal to AB square. AB squared plus BC squared minus 2BC into BD. So this is what we get in case of an acute angle triangle, right? AC square will be equal to AB square plus BC square minus 2BC into BD. If the angle is 90 degrees, if the angle B is 90 degrees, what happens? AC square will be equal to AB square plus BC square. We don't have this minus 2BC into BD. But since the angle is less than 90 degrees, this side AC square should be lesser than what we have in a Pythagoras theorem. So that lesser part here is minus 2BC into BD, right? So if we subtract this, we can get AC square there, right? So that's about an acute angle triangle. Let us now do a similar analysis for obtuse angle triangle. So what we are going to do here again is drop a perpendicular. Let's extend the side BC, right? Extend the side BC and drop a perpendicular from the vertex A, such that it meets at the point D. Let's say this meeting point is D. And angle here again is 90 degrees, right? This is the right angle triangle. Now here again we see two right angle triangles. The first one is ADC, right? Triangle ADC, and the second right angle triangle is ADB, right? So two right angle triangles. Let us apply Pythagoras theorem. If you look at the first triangle, in the triangle ADC, right? What do we get in the triangle ADC? AC squared, the hypotenuse square, will be equal to perpendicular side, that is AD square plus DC square, right? AD square plus the base DC square. Again, the base DC, right? The complete base DC can be expressed as DB plus BC, right? It is DB plus BC. So let us replace it now. We get AC squared equals to AD squared plus DC is equal to DB plus BC square. So when we expand this using A plus B whole square formula, what do we get? BD square plus BC square plus 2 into BC into BD. Yes or no? DB or BD, right? So that square, A square plus B square plus 2A into B. Now let us look at the other triangle, ADB here. Now from the triangle ADB, right, in triangle ADB, we know that AB square will be equal to AD square plus DB square. That's it. Now look at this equation here, AD square plus BD square, right? AD square plus BD square. AD square plus BD square can be replaced with AB square. So let us replace this part with AB square. So finally we get AC square equals to AB squared plus BC squared plus 2BC into BD. So this is the relationship for an obtuse angle triangle. And like we have discussed earlier, if this is a 90 degree angle, if this is a right angle, what happens? We get AC square equals to AB square plus BC square. But this is more than 90 degrees. So obviously the hypotenuse, not exactly the hypotenuse, the opposite side, right? The side opposite to angle B, which is obtuse angle, should be more than what happens in a right angle triangle. So in a right angle triangle, it is AB square plus BC square. But here it is a little more. What is that extra part? 2BC into BD. So these are two important relationships based on the application of Pythagoras theorem for an acute angle triangle and an obtuse angle triangle, right? So just remember these identities, that in an acute angle triangle, AC square will be equal to AB square plus BC square minus 2BC into BD. Whereas in an obtuse angle triangle, AC square will be equal to AB square plus BC square plus 2BC into BD. Let us now look at two other important theorems based on triangles. The first one here is the basic proportionality theorem, and the second one is midpoint theorem. Well, the basic proportionality theorem states that in any triangle, if we draw a line that is parallel to one of its sides, then that line will divide the other two sides in the same proportion. Right? Let's understand this with the help of a simple illustration here. So ABC is a triangle that we have considered, and there is a line PQ which is parallel to the side BC. Right? PQ here is parallel to BC. Right? The line PQ is parallel to BC. Now, as per the basic proportionality theorem, if we can draw a line that is parallel to one of its sides, then that line will divide the other two sides. What are the other two sides? AB and AC. It will divide the other two sides in the same proportion. Now let's say the line here meets AB at point P and AC at point Q. So as per the basic proportionality theorem, the ratio in which the two sides get divided is same. So we can say AP by PB should be equal to AQ by QC. Should be equal to AQ by QC. So this is what is meant by the basic proportionality theorem, right? The simple point is to draw a line parallel to one of the sides of the triangle. It will divide the other two sides in the same proportion. Let's say if we take a line which divides, which is parallel to AB, right? Try and draw a line which is parallel to AB. Let's say this is the line parallel to AB. So it meets AC at M and BC at N, right? This line here we see it is parallel to AB. So what do we see? Since MN is parallel to AB, we can say that the ratio in which the two sides are getting divided will be same. So AM by MC will be equal to BN by NC. BN by NC. Right? So that's the application of the basic proportionality theorem. And the next one here is the midpoint theorem, which states that the line joining the midpoints of any two sides of a triangle will always be parallel to the third side, and its length will be half of the length of the third side. Let's look at this with the help of a simple example here, right? So ABC is a triangle. Now let us assume that P is the midpoint of side AB and Q is the midpoint of side AC, which means P is dividing the side AB into two equal halves, right? So this is equal. AP is equal to PB. Likewise, Q is also dividing AC into two equal halves, right? So the segment AQ will be equal to the segment QC. Now, as far as the midpoint theorem is concerned, it states when we join the two midpoints of two sides of a triangle, we get a line as seen here which will be parallel to the third side. The third side here is BC. So the theorem states that PQ, which is the line obtained by joining the midpoints of two sides, will be parallel to the third side, and PQ will be half of the third side. It will be half of BC. So if we consider P and Q, right? P and Q are midpoints of, right? P and Q are midpoints of AB and AC. Then PQ will be parallel to the third side BC, and also PQ will be half of the third side, half of BC. So that's about the midpoint theorem, and it can be for any two midpoints, right? Let's say if we consider the midpoint of the side BC, let's assume the midpoint of side BC is somewhere here approximately, right? It is equal to M. Right, the midpoint is M. Then if we connect QM, right, the midpoint of AC with the midpoint of BC, we'll get a line QM. Now, as far as the midpoint theorem is concerned, it states QM will be parallel to the third side, which is AB, and QM will be half of AB, right? That's the theorem. So QM is parallel to AB and half of AB. Likewise, if we connect these two midpoints, P with M, right? P with M, what do we get? This line PM will be parallel to AC, and it will be half of AC. PM will be half of AC. So all these are based on the midpoint theorem, right? So we get that QM parallel to, again let me tell you, M is dividing BC in the same ratio, right? These two are equal parts. So QM will be parallel to AB and QM would be half of AB. Likewise, the third part here is PM, right? PM will be parallel to AC and it will be half of AC. PM will be half of AC. So that's about the midpoint theorem. And also one important point that I would like to mention here is that if we look at the midpoints of the sides AB, BC and AC, what do we get? P, Q and M. When we connect all these three, we get a triangle, right, which is PQM, PQM. Now the point to be noted here is the area of the triangle PQM will be 1/4 of the area of the triangle ABC, which means the triangle obtained by joining the midpoints of the three sides will be 1/4 in area of the original triangle ABC here. So we can conclude that area of triangle PQM will be 1/4 of the area of the triangle ABC, right? Well, this is not midpoint theorem, but an important conclusion that we need to remember, which states that when we obtain a triangle by joining the midpoints of the three sides, the area of that new triangle would be 1/4 of the original triangle, right? So that's about the basic proportionality theorem and the midpoint theorem, which would help us while solving questions on triangles from geometry.